Hi, my name is Hannan and my matrix number is 22001419. Today I will present my research on first order circuit application on medical engineering device under subject KIB1012 circuit theory. The device that I have chosen is defibrillator. So we will go through some parts stated in this table of contents here. First of all, I'll briefly explain what a defibrillator is. Defibrillator is a device that shocks the heart with electricity to regain a normal heart rhythm when someone is undergoing cardiac arrest. There are two types, which are implantable defibrillator or pacemaker and automated external defibrillator AED that we will talk more about later. So how do AEDs work? First, we attach electrodes to the patient's chest. These electrodes contain sensors that monitor heart activity. Then AED will analyze the heart activity and determine whether a shock is needed or not. Basically, you can see from the picture that a shock is needed when the heart has an irregular pattern of rhythm. The shock will interrupt the irregular electrical activity of heart and reset and restore a normal one. Sometimes CPR is needed to circulate blood to vital organs because heart activity might stop up to 2 minutes until the pacemaker restores a normal one. We will move on to the important part, which is understanding the first order circuit, in this context RC circuit. RC circuit is basically a circuit that has both resistor and capacitor and characterized by the charging and discharging of the capacitor through the resistor. The term first order refers to the fact that the circuit's behavior is described by a first order linear differential equation, which is from IC plus IR equals to 0 to dV of dt plus V over RC that we further derive until we get Vt equals to V naught exponent to the power of negative T over RC. You can see that it is an exponential decay here. The key parameter is in the first order circuit is time constant or tau. Time constant is the rapidity with which the voltage decreases and the time required for the response to decay to a factor of 1 over exponent or 36.8% of its initial value. How do we determine this? We just apply the voltage formula previously and substitute T equals to tau and tau is equals to RC, and thus the equation will be Vt equals to V naught exponent to the power of negative 1 or 0.368 V naught. From this table, we can see that after 5 time constants, or when Vt equals to V naught exponent to the power of negative 5, the capacitor is considered to be either fully discharged or charged. Note that as time increases, the voltage decreases towards 0, and the smaller the time constant, the faster the response, and vice versa. Now we will take a look at the RC circuit in the defibrillator. Some important elements are a capacitor that stores energy and discharge to generate the shock and resistor that limit the current flow. This circuit also has step-up transformers, as the defibrillator typically operates on high voltage, and a rectifier to convert alternating current AC to direct current DC. Most of the medical devices are in the form of AC, however, the electric shock delivered to heart needs to be in the form of DC. Lastly, an inductor to prolong the duration of the current flow by inducing a voltage that opposes current flow. Did you notice that there is an inductor in the circuit? Then why is this an RC circuit instead of an RLC circuit? We need to understand that only resistor and capacitor are the fundamental elements in the basic circuitry of a defibrillator that involves charging and discharging of capacitor, as we have mentioned earlier. Meanwhile, inductor is only an additional element to prolong the duration of current flow, as it needs to last for several milliseconds in order for heart to completely depolarize. Now, let's take a look at the circuit. We can divide it into two parts, charging part and discharging part. First of all, the charging part. When the switch is connected to point A, capacitor will connect to the power supply and step-up transformer. Note that at least 2000 volt is needed to produce a shock. Then the electrical current begins to flow through the circuit in counterclockwise direction until the voltage at the terminals of the capacitor is equal to the voltage of the power supply. At this point, the capacitor has reached its total charging capacity and the current flowing through the circuit has stopped. From this graph, you can see that when T equals to 5 RC, the current flowing almost 0 and the capacity of capacitor is at least at 99% of voltage of the power supply. Current against time graph is represented by the equation I equals to I naught exponent to the power of negative T over RC. Meanwhile, the potential difference against time graph is represented by the equation V equals to V naught exponent to the power of negative T over RC. This proved our point earlier that after 5 time constants, a capacity is considered to be fully charged. Lastly, we must make sure that voltage capacitance is at least twice the value of voltage needed to produce a shock, but higher voltage rating is always advisable. Next, the discharging part. When switch connected to point B, the capacitor begins to discharge and electrical energy is delivered through the pedals to the heart. The current delivered to the heart must last for several milliseconds, 10 milliseconds on average, in order for the heart to completely depolarize. However, the current of a discharging capacitor decreases exponentially. Thus, an inductor is needed to prolong the duration of the current flow by inducing a voltage that opposes current flow. The amount of electrical energy delivered to the heart can be calculated by the equation E equals to half CV squared. Note that the defibrillator needs at least 400 joule of energy delivered if it is being applied externally. We also need to consider the resistance of electrodes that can range from 15 to 100 ohms. And that's all for discharging part. These are the references that I referred to, and lastly, thank you for sparing your time to listen to my presentation.